All right, Luca, take it away. Thank you.
Yeah, hello everybody. I'm Luca Bertaccini from ETH Zurich. I'm with the PULP platform group there. I'm doing a PhD. And today I'm going to give an overview of our open source activities. We started from an open source ISA to build open source hardware IPs. We bunch hardware IPs together to build platforms. And finally, we have also started exploring open source EDA tools to get to a fully open IC design. So we are a research team. We focus on energy efficient computing architecture. We started about 11 years ago. We're quite a big group, about 100 people. We are led by Luca Benini, who's a professor at both University of Bologna and ETH Zurich. And during all this time, we have designed and tested more than 60 chips, spanning from smaller single-core IoT systems to larger many-core ML accelerators, like the one on the right side of the slide. We have like hundreds of RISC-V cores. You can find information about all our chips on our chip gallery. Here is a link in the slide. And all these hardware architecture are open source. We believe in open source because there are so many benefits. We cannot afford to do everything in-house. So we need to collaborate with many different domain experts, and we can do this thanks to the open source community. Also, we don't have to have long discussion on IP ownership, background IP, everything is in the open, so we can start right away and spend most of our time where we actually want to spend it, which is on the design rather than on the paperwork. We make extensive use of a very friendly license so that anybody can use, change, and make products out of our IPs. And furthermore, you can also see what we have, evaluate us in advance, so everything is there. You can see what we do even before speaking with us. So many, many benefits. We can manage more complex design, have faster collaborations. It can facilitate for us industry and academia relationship, and it allows us to have auditable results, so reproducible results. But how do we get to have fully open source hardware platforms? Well, first of all, we need an open source ISA, otherwise we couldn't be able to open source hardware artifacts related to the processors. And for this reason, we use RISC-V. It has been growing really fast. Now it's about 4,000 members, really changed the picture on computer system research. And it's modern, it's open, it's free. You can also extend it, use it, and specialize it for a specific application scenario by adding new custom instructions. So many, many members, actually many more that I could fit here in the slides. This also means a very wide open source software community around RISC-V. We have many different tools, a very wide software ecosystem that is already there to evaluate and that you can leverage to use your RISC-V hardware systems. So this was a really, really good target for us, and this is what we took. And from here, we started building open source hardware IPs. So what we provide as PULP is a set of building blocks. We have been designing RISC-V cores, 32-bit cores, 64-bit cores. Some of the one here have then been donated to other organizations, like the RISC-V core is now known as CV32E40P under the OpenHardware group. Ariane is now known as CVA6, and this is all this is all great because they're doing a lot of effort in bringing these cores to industrial maturity. We then have a lot of other IPs like peripherals, interconnects, domain-specific hardware accelerators, and we take all these building blocks to build our platforms. It can be smaller IoT nodes like single-core system with either a 32-bit or a 64-bit core. It could be a multi-core architecture with a compute cluster, or even multi-cluster systems. And basically, with this, we can explore a very wide range of hardware architecture, from smaller IoT system to very large HPC design. Again, everything is open source, so in case you're interested, you can visit our GitHub page under PULP platform. You can find there HDL source code, so you will find all the system Verilog files, test benches, SDKs. There are guides on how to build our system as well, so it's all there, easy to use. You can use it, change it, make products out of it. Again, very, very friendly licensing we are using here. And we noticed this was actually very successful. It's been, many of our repositories have been in the GitHub trending system Verilog repositories of the past month. So a lot of users and contributors to this IP, which is great. And it also allowed for many successful industry collaborations. So we had, for example, here eFPGA with Quick Logic, an IoT processor that we designed with green waves, another IoT processor with non-volatile memories that we had in collaboration with Meta and Newman, and again, the very large ML accelerator I was showing before, composed of 2 chiplets, each one with its own dedicated HBM memory, and in total we have more than 400 RISC-V cores, so really a big, big platform. And on top of this, also we've seen that many people have used our work, which is another great point of the open source community, because we see other people could use it and they could enable further research. Already yesterday we saw some of the presentation using Ariane/CVA6. But there are many other examples. I'm just citing a couple here. We have, for example, IBM at the RISC-V Week in Barcelona 2019, Intel in 22, Google in the ISSCC keynote in 2020, and NVIDIA in SPD 23. So this going open source, these open source models really enabled many, many benefits for us as a research group. It had a couple of surprising side effects. We had underestimated at the very beginning maybe the bureaucracy involved, in the sense that we need to get proper approval for everyone if we want to open source something. As a university, we have PhD students and staff, which is paid by the university, so the work belongs to the university, and the university should give green light for open sourcing the IPs. But the same we need to get from master and semester thesis students that might work on projects, and they own the work they produce, so we need to make sure they approve that their work can be open source at some point if you want to upload it on GitHub. Also, many of the agreements with companies were not meant for open source IPs. So instead of having instead of paying for exclusive IPs, we actually need sponsoring agreements. And it's really important for us that we do not sign anything that binds our open source effort. But yeah, so everything we saw so far was mainly on this OpenHardware side. So we had everything open on the RTL level. But we still relied on proprietary PDKs and EDA tools for synthesis and placer route to build our chip. And we actually wanted to move to a fully open source IC design because of the many benefits that, again, open source has. And just to cite a couple, again, we can have reproducible results. We can have new research based on these tools. In terms of education, again, no black boxes. We can really go and show the students how these tools actually work and how is the full process made. So we're starting exploring a bit in this direction as well. First of all, we need open PDKs. Without an open PDK, we cannot release anything beyond RTL. So this is really key. It's also very important because many IPs might contain proprietary information on technology, and without an open source PDK, this could not be released. So this is another very good point. There are some very nice processors already, like Skywater 130 nanometer, IHP 130. Of course, and more advanced 40 nanometer or 65 nanometer open PDK can be a game changer because it could make many viable products could be designed with it, basically. You also need open source EDA tools. We started collaborating with the University of San Diego and with many of the open source EDA tool developers. We have started using Yosys for synthesis and OpenRoad for placer route. We have been seeing that this works really well. Also, they are improving really fast, so it's really, really promising. And let's say even if there is a gap with commercial EDAs in terms of PPA or support, these do allow you to make your own chip, so they're great for many application needs, great for teaching, and this is also why we organized a summer school in June at ETH Zurich, where we will go through open source IC design and computer architectures. There was a lot of interest, so we're really, really happy about it. But how do we put all of this together? So basically, we started from this OpenISA. We built our processors. We built the other open source hardware IPs. We made platform by bunching together these IPs. We started exploring OpenPDK and OpenEDA tools for a fully open IC design. And we implemented it on one of our architectures. This is a full system. It's a Linux-capable RISC-V MPU. We have a RISC-V core there. It's a CVA6, so 64-bit core, about 1 megagate of logic. We have a set of peripherals. So it's a full system that we wanted to implement with open tools, open PDKs, and whose RTL is fully open. So we work on an open source tool flow. We use IHP 130 nanometers as an open source PDK. Then we relied on Yosis for synthesis, which calls ABC for logic optimization and mapping. For placer route, we used OpenRoad. We added a bit of a preprocessing stage to simplify some of the system Verilog constructs, translating them to Verilog before feeding them to Yosis. And we started playing around with it a bit. We saw many very nice improvements in only 6 months in terms of PPAs. So we actually started from the upper right corner right there. And in only a couple of months, we were able to see, like we saw a 1.6 times area reduction, and the maximum frequency improved by 3.5 times. So it's going really, really fast. And while it's not providing exactly what we could have with commercial EDA tools, it's really improving faster. It's really, really exciting. And with this, we built Basilisk. This is a fully open source SoC and the full design RTL to GDS. It's based on OpenPDK, the IHP 130 nanometer, open source EDA tools. We had the chance to collaborate with all the main developers, and we will submit the GDS next month. So we're really excited about it. But yeah, so this is fully open. All these scripts are open. The GDS will be released open source as well. The RTL is open, and this could not have been possible without OpenPDK and OpenEDA tools. So really, really cool things happening. So just to briefly conclude, for us, open source is really a necessity. We cannot afford to do everything in-house. We need to collaborate with many experts. Now we have very complex designs, and this is really a necessity for us. It's very important for us that our results are trustworthy and people can verify it, because it can give a nice plus in terms of research. And it really worked. We were able to get more projects, more funding, thanks to these open source activities. We started many more interesting and fruitful collaboration thanks to it. So we were really happy about it, but also helped other people. So it enabled further research from other companies, individuals, universities. There is already commercial use of our IPs. Some we don't even know about. So really, the open source model was really, really successful for us. And again, everything we do is open source. So if you're interested, go check our GitHub page. We are also on Twitter. We post frequent updates on our research, new releases, and basically you can get up to date with everything on there. And that's conclude my presentation. So if there are questions, I'm happy to answer.
Thank you, Luca. I have a first question. That chip you're going to tape out on the IHP process, so you've closed timing on it, you say 13 nanosecond critical path.
Yep.
What corners do you know? Do you know for STA? Like, what's the state of open source STA sign-off? Different corners.
Yeah, I need to check with the colleague that worked on it, but I can let you know offline.
Yeah, cool.
I will ask you.
And the PULP programs research seems quite broad. You're doing like quite advanced things with, like quite high-tech process nodes, but then you're also kind of like doing relatively less performant implementations here. My question is sort of, where, like, how much as a percentage of the overall program goes into trying to enable the open source EDA flow?
Okay.
Is it just a side thing, or is it like actually a bit of a main thing these days? Or?
I mean, as I was showing at the beginning, we're a very big group. So we have a part of the group that is working on it at the moment. We are still working also on like relying on proprietary PDKs and and tools for other projects. This is thing that kicked in about a year ago. Yeah. So it's a fairly recent project, but again, it's looking really, really promising. So we are putting efforts into it and increasing the efforts around it at the moment. But yeah, I don't know how to give you an exact percentage of.
This is great work. I think you got a lot of logic packed in there, and it's what's 13 nanoseconds? It's like 60 odd megahertz, 70 megahertz, something like that. So
yeah, it's
pretty good.
More, yeah, but
yeah.
Very big system. Also, it's stressed a bit the open source EDA tools because it's again 1 megagate of logic.
Yeah, yeah.
So then you have a bit further challenges that you have to take into account and you can show.
Sure, but this is a good example of a more sort of, like what real products sort of have in them, right?
Yeah.
IoT kind of things. Awesome, thanks. Olaf, sorry.
2 quick questions. So you said the GF 500 nanometers. Is that correct, or should that be 180?
180 should be open, yeah.
You had IHP 130. Yeah, this.
Okay. Yes, I also need to double check. I think 180 might be.
Yeah. Okay. And
we use IHP for this.
Okay. And was that Bianca or Charlie on the last page?
Yes. It was. It's Charlie.
Okay. Thanks.
Did you find any challenges with the memory controller? Or so there's a memory controller. Is there like an Ethernet or anything like that? I didn't see.
Yeah, at this stage we don't have an Ethernet in this system.
Okay. So but the memory controller. So we now have an open memory controller that you're going to tape out, and we'll have real performance benchmarks after you bring up Linux.
Yeah.
Tim.
So like the Sky 130 open source PDK has been around for like 3 years now. Why did it take you 3 years to go to open source tools and open source PDKs?
Yeah, so I think we also consider the Skywater 130. I don't think we were able to fit in a slot for the MPW shadow. So I don't remember if it was because of the size of the system or something. I need to also double check with my colleague, but I can let you know offline. Thanks.
For CVA6, for synthesizing that, what pre-processing are you doing before putting into Yosis? Because I've tried and I can't get it to work.
Okay, so for us, it's really, yeah, we have a bit of pre-processing stage where we simplify a bit some of the constructs that are not supported by Yosis. Yeah, there are a couple of more details if you want. I also have some other slides in a different.
Is it mostly manual that you go in and pre-process it, or is it?
No. We have everything automated on the. So we have built a couple of tools to fix this. But if you want, maybe in the coffee break, I can show you a couple of more details.
All right, I think we'll leave it there. Thanks very much, Luca. Cheers.
Thank you.
Nice work.